Okay, let's begin now with exponential and logarithm equations and solving these. All right, so exponential equations. Nine problems altogether. Let's begin. First, we have 6 to the 2x equals 6 to the 1 minus 3x. So I just equate the powers. And solve like a regular linear. Just like that. And we check. And there you can see that's correct. X is 1/5. Okay, just opening up the solutions for the next few. So in the second one, 5 to the 1 minus x is equal to 25. It pays to know what are known as your perfect powers. Your perfect powers. That includes all the square numbers, all the cube numbers, all the fourth powers, fifth powers, sixth powers, and so on. Not the first powers, however, because every natural number is a first power. Those are known as perfect powers, that set of numbers. All right, so 25 is 5 squared. Therefore, I can rewrite the equation as 5 to the x minus 1 equals 5 squared. Then I equate the powers, so x minus 1 is equal to 2, and then you just solve. So x is equal to 3. Wait. Did I just make a big blunder? Oh, sorry. Beg your pardon. I wrote it down wrong. It says 1 minus x. I don't know where is my head? 1 minus x. And if 1 minus x is equal to 2, if 1 minus x is equal to 2, then negative x is equal to 1, and therefore x is equal to negative 1. There. That fixes it. Good. Okay, so I think this is saying 8 to the power of x squared equals 8 to the 3x plus 10. Now, you might say, wait, how do I know if it's this or this? Like, which one is it? Well, if I do this, if I were to interpret it this way, like going from the bottom up, from the bottom of the tower of powers up, then it wouldn't be a very interesting operation. It wouldn't be a very interesting default way to interpret it, because, as you know, this would just become 8 to the 2x, which is not very good. So we actually, when you have a tower of powers, like 3 to the 4 to the 5 to the 6, you work your way down the tower. So you do 5 to the 6 first, then you do 4 to the power of that, then you do 3 to the power of that. Okay? Okay, with having stated that, let's now solve this. So we just equate the exponents. So x squared is equal to 3x plus 10. Putting it all to one side, x squared minus 3x minus 10 equals 0. And then solving like a quadratic, x minus 5 times x plus 2 is equal to 0. And then we can see that x is either 5 or negative 2. That's the only way that can be true. And indeed, if you pick up these numbers and substitute them in, you'll see that that's true, because this will turn into 8 to the 25, and this will turn into 8 to the 25 as well. Whereas if I put in negative 2, this will turn into 8 to the 4, and this will turn into 8 to the 4 as well. So that's my answer to the third one. And you can see that's right. Those are the two solutions to that equation. Next, we have 7 to the 4 take x equals 7 to the 4x. So we just equate the powers. And this means that 4 equals 5x. And therefore x is equal to 4 over 5, 4/5, or 0.8. Now, what do we do about this one? 2 to the 3x is equal to 8. 2 to the 3x, sorry, 2 to the 3x is equal to 10. What do I do? Well, take logarithms of both sides. So if I do log base 2 of 2 to the 3x, what is this expression saying? It's saying, to what power do I need to raise 2 in order to get 2 to the 3x? Well, the answer is obviously 3x. Right? And so if I take logs of both sides, log base 2 of both sides of the left side and of the right side, then I'll end up with 3x on the left and some number on the right. Some number on the right. The number in question is a little bit over 3. It's going to be between 3 and 4, because 2 to the 3 is 8 and 2 to the 4 is 16. But how do I find the actual number itself? You would need a calculator. Let's just suppose that I don't have access to this fancy custom logarithm button. The one that looks like this, with a little box down there for the base and a little box right there for the argument to put in. Let's suppose that I don't have a custom logarithm button. And instead, what I have is either a common logarithm button, which has a secret little 10 down there, log base 10, or a natural logarithm button, ln, like that, which is really log base e. Let's suppose I only have one of these buttons available to me. What do I do? You can use the change of base formula. And it says that this is log 10 over log 2. And wait, I want to find out what x is, right? Not what 3x is. Okay, just divide that by 3. Divide the right-hand side by 3, and therefore the 3 will appear here. just like that. Not for any particular reason, but I mean, this is almost like showing off at this point. But you see that 3 right there? That can be brought up here. So it becomes log of 2 to the 3. So instead, this can now be written as log 10 over log 8. But wait, don't we know already what log 10 is? If it's the common logarithm, log base 10 of 10, well, that's just 1, isn't it? Right, it is. So it's 1 over log 8, right? 1 over log 8. And indeed, that's sort of like enough just playing around with it. Let's now calculate. Where's my calculator? Right there. So we get around about 1.1073. Let's check and see if that's actually right. So what I type in my calculator is 2 to the power of, and then I open my brackets, and then I type in 3 times 1.1073, and close my brackets, and I get 9.9098, which is good enough. All right. Oh, and indeed, I was supposed to just make sure. Yeah, that's fine. All right. Let's now look at the problem 6, 7, and 8, and 9. Problem 6. Now, instead of having a nice whole number over here on the right, now we have 7 to the something and 4 to the something. So what the heck do we do? Well, you can take logs of both sides, why not? So if I do log base 7 on both sides, I guess I've actually kind of forgotten how to do this. But, you know, I'll try stuff. See if I can get there without, see if I can jog my memory. Okay, so I end up with this. And then I notice that I have a power of 4 inside the brackets, right? Well, I can move that power out to the front. So 1 take x is equal to 3x add 1 times log base 7 of 4. And then I have, what do I have? Well, I have a rational expression being equal to some particular number, don't I? And then I think to myself, wait, did I just do the right move there? Indeed, now I have x mentioned on just one side, but you know, whenever I do these things, don't I really want it like this? And I try to get all my x's together with no division involved. Indeed. So that's what I'm going to do. So here I go. One take x on the left. Three x log base 704. Right, here's how I'm going to do this. Let's do this right. There. And now I see that x is mentioned there and there, whereas these are just regular numbers. So I'm going to get everything together. That's getting everything on the left. This is getting everything on the right. Now let's factor out the x. I mean, this is a bit long-winded how I've done it. That's fair enough. And the last move is just divide everything through by x. Yeah, really long-winded, but I think we got there in the end. And this is where I remember that my calculator doesn't have a custom logarithm button, even though it's a scientific calculator. Can you believe it? So I'm actually going to get an approximation to this. And I get 0.7124. And so I get this really, really small number. Is that right? I mean, I feel like I entered everything correctly, but we're about to see. No, that's actually bang on. That's totally accurate and correct. All right. Now for the 7th problem. Okay, I'll take common logs of both sides. So log 9. There. I think that's correct. Okay, yes, that's the exact answer. And there's the approximate answer. Exactly. All right, now the 8th problem. E to the 7 plus 2x. Take away 3 is equal to 0. So straight away, I rearrange. I take natural logs of both sides. Divide by 2. There's the exact formula. I like that. And that's correct, 40p. All right, and just the last one here to clean up. Finish up, brother. First, I'm just going to take away the 11 from both sides. We're 9. And natural logarithm of both sides. So 4 minus 7x is equal to 9. Or rather, 4 minus 7x is equal to ln of 9. And so ln of 9 minus 4 over minus 7. Okay. There. Okay, so I wouldn't have negative 7 in the denominator. I would actually, yeah, personally, I just don't like to have negatives in the denominators of fractions. But anyway, all that is all done. Okay, and where to next? Logarithm equations. Logarithm equations. Right, so 9 problems, better get cracking. Better get to solving. Okay. Log base 4 of that is equal to log base 4 of that. So what do? I just equate the arguments. x squared minus 2x is equal to 5x. Take 12. Move everything over to one side. So x squared minus 7x plus 12 is equal to 0. Solve like a quadratic. And then we obtain the solutions of 3 or 4. Let's open up the first 3. Next one, this is saying that log of 6x over 4 minus x is equal to log of 3. And then I equate the arguments, and so 6x over 4 minus x is equal to 3. And then I'm going to multiply that up there. Nine x is equal to 12. So x equals 12 over 9 or 4 over 3. And I'll check upon solving the third one. So these are I'm adding a pair of logarithms now, and therefore I'm multiplying the arguments. So ln of x times x at 3 equals ln of 20 take 5x. And so now I just equate the arguments. So x squared at 3x is equal to 20 take 5x. So x squared at 8x take 20 equals 0. And so I say x at 10 times x minus 2 is equal to 0. So that x is equal to 2 or negative 10. And now I should check their solutions. Everything must be checked. Everything must be checked. And we see that 3 and 4 both work. But we can see that there is a sensitivity that we have missed. We are not permitted to have negatives as arguments in logarithms, right? So we've got to think about this carefully. So we think that x is 4 over 3. Does that work? It seems to be just fine for the first one. What about the next one? Well, 4 minus 4 over 3 is 4 take 1 1/3, which is 2 2/3, which is fine. So that's all good. But the next one is where we have to take extra special care, because look at this. 2 works just fine. What about negative 10? No, it does not, because you cannot have the natural logarithm of negative 10. This is impermissible. So this is a fake solution. And now we check. Okay, you can see that x is equal to 4/3 in the second problem. And in the third problem, look at that. Negative 10 is reason to not be okay. But 2 is just fine. And these are very important remarks here about how to think about these false solutions. Like this negative 10 here does solve that equation and that one and that one. But, and this one, in fact, even, but not the original one, which is the very equation that we're trying to solve. Okay. All right, let's try problem 4. Log base 3 of 25 take x squared is equal to 2. So what I will do is 3 to the power of both sides. So I'm going to have 25 minus x squared on the left. And 3 to the power of 2, well, that would be 9. And then I'm going to take 9 from both sides. So I have 16 minus x squared is equal to 0. And then I observe a difference of 2 squares. There's my first square, and there's my second square. And this is a difference of 2 squares. So I write 4 minus x times 4 plus x. And what solves that? Well, what solves that is either x is equal to 4 or x is equal to negative 4. But then we check based on the original equation. So 4 appears to work just fine. And so does negative 4. In fact, this one, you didn't actually really need to do any of that stuff. Right? Because obviously 25 take x squared is 9. Like, but anyway, I mean, that's fine. That should be fine. Okay. 5th problem now. Okay. We've got to combine these logarithms. Log base 2 of x add 1 over 2 take x. Set that equal to 3, just like that. Then do 2 to the power of both sides. Two to the power of 3, well, that would be 8. Then x add 1 is equal to 8 times 2 take x. So x add 1 is equal to 16 minus 8x. So 9x is equal to 15. So x is equal to what? 15 over 9, which is 5 over 3. And does that seem fine? Well, it's 1 2/3, which works for the first one and works for the second one. So it seems fine to me. But we'll see after the 6th problem, won't we? All right, so a pair of logarithms, both base 4. They're being added together, and therefore we multiply the interior arguments together. So log base 4 of negative x multiplied by 6 minus x, close brackets, set that equal to 2. Then do 4 to the power of both sides. So we're going to have negative x, open bracket, 6 minus x equals 4 to the power of 2, which is 16. And then guess x squared minus 6x. Bring that 16 over, so we get minus 16 equals 0. Factorize it just like that. And get your supposed solutions. But then check them. Does 8 work? No, it does not, because you have negative 8 right here. And negative 2 right here. So that is a false solution. Does negative 2 work? Yes, and yes. So now we check. Everything must be checked. Okay, the 4th one is correct. The 5th one is correct. And the 6th one. That is also correct. All right. 7, 8, and 9 remain. Let's get to solving 7, 8, and 9 then. Okay, I'm going to move this to the left. This negative log of x take 21, I'm going to move it to the left-hand side. So I get log of x plus log of x take 21 is equal to 2. Then I have a sum of logarithms. So I multiply their arguments. Just like that. Then I want to get rid of the logarithm. So I do 10 to the power of the left side and 10 to the power of the right side. So I get this. Then expand. And set it equal to 0. And then can this be factorized? Let's see, we've got 2 and 50. No. 4 and 25. Yes. So it does work. Just like that. Just like that. But are these valid? Well, the answer is no for that one. That's false, because we cannot do log of -4. That's not permitted. And 25 appears to be totally fine. But we will check it in a short while. Problem 8. Same strategy. Move the natural logarithm here, ln of 3x at 2. Move it to the left-hand side. So ln of x take 1. Take ln of 3x at 2 equals 1. Now we have a difference of logarithms, so form a quotient of their arguments, just like that. Or a fraction, if you like, whatever. Then do e to the power of both sides to get rid of the natural logarithm. Okay, getting close. Bring this up here, just like this. You want the x terms by themselves, so you're going to have to expand, I'm afraid. Bring them over here. Bring that -1 over there. And factor out x. And then divide. And there you go. Whatever this happens to be, that's the answer, I believe. But I'm going to calculate it. Wait, are you kidding me? I don't have... What? This has got to be a joke. Seriously. I don't think it has E on this calculator, and this is supposed to be scientific. What? Okay, I'll just get on with it. Wait a minute. Let me actually try something, because I think this works. Okay. What if I just type in E alone? No, you have to do that every single time. If I want to write E on this calculator, I have to write E1. But anyway. Anyway, okay, get on with it now. So 1 take 3 E1. And here's what I get. That's what I get. That's problem 8. But there's one more to do. One more to do. And then we check. Everything must be checked. Difference of logarithms, but hold on just a minute now. There's a 2 right here. You have to contend with that 2 before you do anything. If there's a 2 in front, that comes up and it forms a power. Because don't forget, 2 log x is exactly the same as log x plus log x, which is exactly the same as log of x times x, which is the same as log x squared. That's why the 2 comes up there. All right, so we have log x squared right there. Take log 7x, take 1, and that's equal to 0. Then log of x squared over 7x, take 1, is equal to 0. Then get rid of the logarithm. But how? Do 10 to the power of both sides. 10 to the power of the left side and 10 to the power of the right side. 10 to the power of the left gets rid of the logarithm. 10 to the power of 0 is 1. And then just solve like normal. Okay, but hold on just a minute now. Can this be factorized? No. Wait, do the discriminant. So we get 49 minus 4 times 1 times 1, which is 41. So it does have solutions, but they're just not pleasant solutions. So let's get them. I will do completing the square. There. What's 1 minus 49 over 4 is 1 minus 12 and a quarter, which is negative 11 and a quarter. Move to the other side and we get 11 and a quarter. 7 over 2 plus or minus 11 and a root of 11 and a quarter, just like that. But 11 and a quarter, excuse me, isn't that 45 over 4? So isn't that actually like a little bit more pleasant than what you think? Oh, yes, it actually is. And the square root of 45, well, that's the square root of 9 times the square root of 5, which is 3 times the square root of 5. So it's actually really not so bad. It looks a lot better than what I thought. And then we bring this together like this. But wait a minute, what happened to the minus sign? Well, what did happen to the minus sign? 3 times root 5. Let's calculate. 6.7. Wait, does this work? Does that actually work? Because that gives me, if I take if I do 7 minus 3 root 5, I do get a positive number. And so there's no problem at all over here. But is it okay here? Well, I have to investigate. So I'm going to do, first, I'm going to find out what 7 minus 3 times root 5 is. And then I'm going to divide it by 2. Okay, that's good. Then times it by 7. Then take 1. And I get a positive number. So in my opinion, both solutions are valid. But we'll soon see if I'm wrong. We'll soon see if I'm wrong. Because now we check. Everything must be checked. Okay, all right. 25 is the only solution, and that's correct. They end up with the exact solution that I did. And there's their approximation. That's correct. And last, this one. All right, so they get these same solutions I do, and they notice that was pretty darn small. And they checked, and that is okay, and that's okay, and that's good. Okay, so they're all complete. They're all complete. We'll save it. And try the next thing, which is applying all this, putting it into action. Okay. Oh no. I haven't done this in ages. Oh well. Right. So I'm not going to call this just simply applications, because that's kind of vague. I'm going to call it this. There. 1. We have $10,000 to invest for 44 months. How much money will we have if we put the money into an account that has an annual interest rate of 5.5% and interest is compounded quarterly, monthly, continuously? This one I can do. This one I can do. This one I have forgotten. I've forgotten it. So what I'm going to do is 1 and 2, and then I'm going to read the notes, and I'm going to remind myself how to do 3 before I check the answer. All right, so quarterly, huh? That means every 3 months, right? So what's 44 divided by 3? The answer is 14. 14 quarters have passed. 14 quarters have passed. And, you know, if it just updates the bank, if the bank just sort of, is it a bank? If the account is just updated every 3 months on the dot like that, then it would be 44 over 3 rounded down. And it would be that many updates. right? And so what I would do is multiply my initial investment, which is 10,000, by 1.055 14 times. So put a 14 up there, and I get an approximation. And because it's currency, 2 decimal places, please. That's what I think you have to do. But the only way to know is to check. So $21,160.91. And if it's monthly, wait, no, that's complete and utter garbage. What I'm saying is complete and total garbage. Completely ignore that. Okay, I've forgotten how to do this. I have to read. I'm not going to write garbage. Let's see. What? Not now. Okay. Does this make sense? Hmm. $100,000 principal. That's P, right? That's what P stands for. Quarterly. So what do they do? Right, they get the rate, which is 0.075. And it makes sense that you would add on 1 to that. But then what they do is they divide that number right there by 4. So the 5.5% that we were working with before, if it was that's an annual interest rate, but if it was going to be modified to be quarterly, I'd have to divide it by 4. Okay, that makes sense. And wait, 54 months, which is 4.5 years. Okay. But then you have to figure out how many quarters are in 4.5 years. So they just multiply by 4 to get 18. And 54 divided by 3 is 18. So that would actually be completely fine. Yeah, no, okay. I think I understand that. And if it's monthly, 12 there, 12 there, that makes sense. And if it's continuous, what do you do? That special number which you are compounding now becomes E. Yeah, that would make, would that make sense? No, I'm going to have to learn this as a special case, as I don't quite understand how that just sort of goes like that. Why is it turned into 4.5 though? Not 54. Okay. You know what? I'm going to do this example here. And if I get it, then I get it, right? Because I don't want to waste the problems on. If I don't understand them, I'm not going to get the answers, right? So that would just be a waste. So I need to do this example here and see if I get it. So there's P, the principal amount. It's put into account that earns an interest rate of 12%, so 0.012. If we want to have $4,000 in the account when we close it, how long should we keep money in the account if we compound interest continuously? All right, so it's this equation, isn't it? That's like the account. So the account is 2,500 multiplied by E to the power of 0.012 T, right? And A in this case is our goal. So there I'm going to put 4,000. And then what I will do is I will divide both sides by 2,500. So I get 40 divided by 25, which is 8 over 5, which is 1.6. So there. Common logarithm on both sides. Both sides over 0.012. And compute. Thirty-nine years. Come on, man. Where did I go wrong? Oh my goodness. I didn't divide it by 10. Of course. There. That's more like it. All right. Now we compound interest 6 times in a year. So what do you do in that situation? In that situation, you I can't believe that I completely forgotten how to do it. Just keep trying. So P, open brackets, 1, that makes sense, plus the rate, however many times it is per year. The rate over a year, over the interval, and all of that to how many years times by how many intervals. Try it. So it's 2,500. Open your brackets. 1 plus the rate, which is 0.12. Get it right this time. How many times per year? 6 times per year, that is. How many years? You don't know, but you do know it will be 6t. And your goal is 4,000. I think that's okay. Divide both sides by 2,500. So just like before, we get this. What's that? That is 0.02. So just do the whole thing as that. Then this. Then what? That should be right. Okay, because my calculator doesn't have a custom logarithm button, I'm going to have to do it the long way. So log 1.6 divided by log 1.02. And then all of that divided by 6. This, is that right? Oh yeah, it did it. All right. You know what? I really want to understand this. So I'm going to read these. There are many quantities out there in the world that are governed, at least for a short time period, by the equation Q equals Q0 e to the kt, where Q0 is positive and is the amount initially present at t equals 0, and k is a non-zero constant. If k is positive, then the equation will grow without bound and is called the exponential growth equation. Likewise, if k is negative, the equation will die down to 0 and is called the exponential decay equation. Short-term population growth is often modeled by the exponential growth equation, and the decay of a radioactive element is governed by the exponential decay equation. For example, the growth of a colony of bacteria is given by this equation, Q equals Q0 e to the 0.195 t. If there are initially 500 bacteria present and t is given in hours, determine each of the following. How many bacteria are there after half of a day. So I'm going to do it. Okay, so Q equals 500. That's the initial amount. Times e to the 0.195. Here, t is in hours, and so half a day means I multiply by 12. And it will be that many, but I'll compute in a second. How long will it take before there are 10,000 bacteria in the colony? So now, here's my goal state, 10,000. And my job is to compute t in this, and that will tell me the amount of time in hours. And the way I do that is 10,000 over 500, which is 20. And then natural logarithm of both sides. And then both sides divided by 0.195. All right, so calculate. So according to this, it's about 5,191 to the nearest bacterium. So, all right, solve this. Okay, ln 20. Divide that by 0.195. And we get 15.36. So that's how many hours is it? What's 0.36 of an hour? Well, 0.1 of an hour is 6 minutes. I don't know why I'm calculating this. It's about 24-ish minutes, something like that. 15 hours and 24-ish minutes. Let's just see. Okay, that's fine. That's good. And that's also good. All right. Carbon-14 dating works by measuring the amount of carbon-14, which is a radioactive element, that is in a fossil. Does it? I thought that it was only valid for a few thousand years. All living things have a constant level of carbon-14 in them, and once they die, it starts to decay according to this formula right here, where T is in years, and Q0 is the amount of carbon-14 present at death. And for this example, let's assume that there will be 100 milligrams present at death. Okay. I really can't wait to do the earthquake one, because I've never done it before. All right, let's see. Okay, so just Q equals 100 times e to the negative, and this is a lot of zeros, times 1,000. Okay. So the answer is 88.34 milligrams. Milligrams? How do you do that? Just mg, right? then how long will it take for half of the carbon-14 to decay? All right, so this is finding the half-life, isn't it? That's quite cool. 100e to the, and this is the number that we don't know. Okay, so just quite literally just do this. I guess regardless of whatever the initial amount is, it will always be ln of a half, right? And so ln of a half must be very special. But anyway, we will divide it by this. And that will give us t. And this we approximate. And then we get 5,589. It's very close. 0.9 years. We'll round it to 1. Let's see if this is right. Yep, that's correct. And that's correct as well. That's the half-life of carbon-14. That's great. Now, this is the one that I really wanted to do because I've never done it. The Richter scale is commonly used to measure the intensity of an earthquake. There are many different ways of computing this based on a variety of different quantities. We are going to take a quick look at the formula that uses the energy released during an earthquake. If E is the energy released measured in joules during an earthquake, then the magnitude of the earthquake is given by this. 2/3 of log E over E0, where E0 is 10 to the 4.4. So let's do it. If this many joules of energy is released during an earthquake, what was the magnitude of the earthquake? Oh, right. 2/3 log 8 times 10 to the 14 over 10 to the 4.4. And then just compute. .3354. Oh, darn it. What? Why? Oh, I see. Okay, I missed out a single digit. Okay, there. That's better. 7. How much energy will be released in an earthquake with a magnitude of 5.9? Let's compute. Wait. Let's see if I can do it without looking. without looking? No, because it's right there. It's right there. Okay, I wasn't looking. Okay, so 5.9 is equal to 2/3 log. And this is the quantity of energy that we don't know. And E0 is like some default or something, 4.4. And that's what I've got to compute. Okay, so I think you do 5.9 times 3/2. And do 10 to the power of that. And then times it all by 10 to the 4.4. And that should be good, right? But that's so large. That's 10 to the... So what? 1.778. That many joules? It can't be. No. That's actually reasonable because that's 14. That's 13, right? So we're going to see. Okay, not bad. Not bad. That's fine. All right. So the real thing, though, that I've been avoiding because I find it hard is compound interest. So let's break it down. What do I really have to know? Well, I have to know this one for continuous. And I have to know this one. Open my brackets here for discrete. That's what I need to know. For the exponential growth and decay equations, I mean, they seem pretty natural. I don't think I really have to know those. They were fine. All right. Let's just do it. Round 2. Okay. I'm ready for you. Let's grab this. Put it here. Round 2. There's the initial investment. There's the amount of months. Okay, so it is, if it's quarterly, 10,000, 1 plus what would be the rate, which is 5.5%. So this much. And it's quarterly, so that means 4 times in a year. And then like the amount of years multiplied by the amount of quarters, right? And 36 at 8 is 3 2/3. So it's that many years. And m is 4. So I think it's this. I think. And now it's time to do it. Divide that by 4. 275. And then again, 1375. Right? And then 4 times 3 2/3. That 1 over 3, 44 3.